solving exponential equations using logarithms. So this gets a bit confusing, this lesson, because we can actually use a number of different log bases to solve these equations. But before we get into that, Euler's special number e, we've talked about it a little bit before. It's around about 2.718. That does come up a bit as technology generally uses log base e as its standard, but we can use log base anything really, particularly when solving these by hand. So it's probably easy if we just get into an actual question for this. So if we were trying to solve 4 to the power x equals 3, and we're trying to find out what x is, we can't express 3 as 4 to the power something. So that's what we might have done previously to be able to solve from there. But in this instance, we can pick what our log base is going to be. So we could use, as you can see here, log base 4, log base 10, or log base e. But it really could be anything we wanted. That's the way that these logs work. Generally, we're going to try and use log base whatever our base of the power is. So log base 4, you can see, comes out with quite a neat answer of log base 4 of 3. So by hand, that's probably the best option of what we're doing here. We can use log base 10, that's kind of a standard practice if you're doing this by hand, but you can also use log base e, which the calculator writes as ln. So I wrote about that a little bit there. That is an ln. But as you can see from what the CAS spits out, all of these answers that I found here give the same decimal value. They are the same. We can even do, solve on the CAS to find out what these values are. But it does use log base e, whereas generally we try and use the same log base as we're given in the question. So in this case, 4 would be my ideal option. When you start sketching exponential equations and indeed logs, you'll need to be able to solve using logarithms in this process. Let's get into some examples and hopefully this will start clicking together for you. So here we go. There is an order of operation for these questions, so you do need to make sure you're getting it in the right order. Lots of different ways we could do this. So 2 to the power x equals 7. I would apply log base 2 to both sides. We can then bring our x down using our log laws, giving us x log base 2 of 2 equals log base 2 of 7. And log base 2 of 2 is just 1, so we're left with x equals log base 2 of 7. Again, we could use log base e or log base 10, but I think that's the neatest way to do this question. So here we've got 1.1 to the power x equals negative 80. So we can have 1.1 to the power x. We're going to divide both sides by negative 4. So that's going to give us 20 over here. We can have a decimal as our log base, as weird as that kind of can look sometimes. So log 1.1 of 1.1 of x equals log 0.1 of 20. And I'm just going to jump straight, knowing that that is 1, and I'm bringing my x down. So x equals log 1.1 of 20. Same thing here, so dividing both sides by 50 gives us 3 to the power x equals 2. I'm going to use log base 3, so I'm using my base of my power to work this one through. So log base 3 of 3 to the power x equals log base 3 of 2. So x, bringing our x down, that equaling 1, x equals log base 3 of 2. So on our CAS, you can see that if we actually solve that, it gives us the solution of log base e of 2 over log base e of 3. You can actually write ln on your test as well. You don't have to write it as log base e, but anyway, that is the more accurate result. That is our exact value. But if a question asks for decimals, then that's when we would answer in decimals. So it sometimes feels that this isn't the most accurate answer, but that is as close as you can get. That is the exact value of that solution. We only do decimals when a question specifically asks for decimals. So getting a little bit more challenging here, you can see we have 0 equals 2 times 10 to the power x minus 4. So this is an exponential equation. In year 11 and 12, you'll be expected to sketch these and things, but it's the same kind of thing. So we're going to add 4 to both sides, giving us 4 equals 2 times 10 to the power x, dividing both sides by 2. Oops. 10 to the power x. So I'm going to use log base 10. And again, our x is coming down. That equals 1. So log base 10 of 2 equals x. So imagine sketching. That's a fairly challenging point to locate. I don't know what that would be as a decimal, but again, we know it's positive, and therefore can kind of work a little bit from there, and you'll see that when you start sketching these a little bit. Solve the following for x once again. So we've got negative 4 equals negative 2 times 2 to the power x. That's going to be 2 equals 2 to the power x. And I guess we can still use logs for this, so we've kind of done these the hard way, I guess, to some extent, but log base 2 of x, our x is coming down, that equals 1, and so does that, so 1 equals x. That's my final result for that question. A little bit of physics coming in here. So the half-life of a substance is the time it takes for a substance to reduce to half its original mass. So you might have seen that with uranium or nuclear waste, half-life. It's quite a long time. Find the half-life of a 10 kilogram rock if its mass reduces by 1% per year. So our original amount, and I've just written it out in this form so you can kind of see how I'm constructing my equation. My original mass is 10. And by multiplying by 0.99 every year that passes, I'm reducing it by 1% each year. So we haven't really covered this in a huge amount of detail, but hopefully that makes sense. So when we're talking about a half-life, so how long will it take, how many years will it take to get down to half of its current mass? Half of its current mass is 5, so that's where I'm getting that 5 from there. And if we solve that on our CAS, we get 68.9676, but I would state that as 69 years. Because when it's at 68, so if I rounded it to 68, then it's not quite at its half-life, so it's after 69 years, it's a little bit past the 5 kilogram weight, or it's reduced more. It's a bit confusing, but there you go, that's what we're getting there. This next one, a little bit tricky again. So find the half-life of a 20 gram crystal if its mass reduces by 0.05% per year. So our original mass is 20. Half of 20 is 10. So that's what we're trying to get to. And we've got 0.9995. So that is a reduction of 0.05% per year. Solving on our CAS, that is 1,386 years, so quite a long time.